Has life been changed after your PhD? You obtained your PhD. You feel
Well,
better?
I mean, yeah, no, this is my first official day as being a postdoc since I submitted my thesis last night. So it's like messaging Matt. I'm like, hey, I'm gonna be paid tomorrow, right? Like, I'm still paid. He's like, yeah, don't worry. Okay.
Your last name pronounces Cesarotti? How do you pronounce it?
So I say Cesarotti, which is a horrible American pronunciation of the actual Italian name. But when I try to speak Italian, I just embarrass everybody. So
Isn't it Cesarotti? I don't know. Is it more
yeah,
Italian?
it's like the CE makes a ch sound. So it's like Cesarotti or something like that. But I speak terrible Italian, so you shouldn't. I always embarrass people. Like an Italian person will be introducing me. They're like, oh, how do you say your name? And I'll be like, Cesarotti. And they'll be like,
I'm sure people will watch the recording. Let me also press the recording and gradually we should start. How long will you be your talk roughly? Do you know?
About 50 minutes.
Or 15 minutes? It can be as long as 90 minutes. So take your time.
Oh, I'm not gonna do that. Howard's like, I'm not sitting through a 90-minute talk. It can be as long as short as the audience wants, I suppose.
Okay.
Surprising that Zoom doesn't have like a throw tomato option, you know?
By the way, at some point my image will disappear because I'm going to move to another spot. I'll be watching.
All right, I won't take it personally, I promise.
Okay. Welcome, everyone. Welcome to Harvard CMSA Quantum Math and Physics Seminar Series. Today, we are very delighted and very honored to invite Dr. Cari Cesarotti. She can correct us. To
You're
speak.
great.
I'd like to congratulate her for her achievement recently complete her PhD and her first seminar after her thesis defense. She'll be speaking about her recent work on oblique lessons from a measurement at CDF2. Let me remind the audience, please feel free to ask questions and interact with Cari during the talk. And it's all please take over. Thank you.
Yeah, thanks so much, Stephen. So like was mentioned, I just defended my thesis a couple of weeks ago. So I'm currently a grad student at Harvard and I'm moving to MIT in the fall. And this is some work that I did with my collaborators, Puya, who is a postdoc at MIT moving to Oregon, grad students Katie and Aditya, and another Harvard postdoc, Sam. So you may have heard recently that there was some excitement in a CDF2 measurement, which is the experiment that used to run at Fermilab, for an anomalous W mass measurement. So today I'm going to walk through what the W mass is, why this was interesting, and how we can use this measurement to sort of parameterize new physics prospects, and hopefully what kind of models might be responsible for such an anomalous measurement. So the outline of my talk today, and of course, feel free to interrupt me at any point with questions. First, since I wasn't sure the scope of the audience, I want to take some time going over the history of the W mass, why this measurement is particularly important for new physics and standard model confirmation. Then I want to talk about what we call the electroweak precision fit. So this is the method in which we actually test how well the standard model prediction for the W mass is met. And then we'll talk about some new physics interpretations of this anomalous new measurement. And then we'll wrap up with some discussion and what can be done in the future regarding this hint of new physics, which is the W mass. So let's get started. First with the history of W mass. Okay, so the W is a gauge boson of the Standard Model, meaning it's got spin 1, and it is the force carrier for the one of the force carriers of the electroweak force. So in the Standard Model, our symmetry group before spontaneous symmetry breaking involves this SU2 left gauge force times a U1 Y with a hypercharge. So then after the process of spontaneous symmetry breaking, we are left with only one U1 unbroken gauge force, and that is electromagnetism. So this means that we have 3 + 1 gauge bosons, and then we go into 1 massless gauge boson after this period, or after this process of spontaneous symmetry breaking. So the way that that works is that we have a Higgs boson, which before breaking is given in this representation. So it's a singlet under color charges. It's an SU2 doublet, meaning it has 4 degrees of freedom. It has a 1/2 hypercharge. So after this process of spontaneous symmetry breaking, 3 of those degrees of freedom are reorganized into massive gauge bosons. So they become the longitudinal degrees of freedom for the W boson, for the Z boson, and then we are left over with 1 massive Higgs boson as well. So the reason that the W mass measurement has been so important is before we actually observed the Higgs boson discovery in 2012, is we weren't sure that this was the correct pattern of symmetry breaking of the Standard Model. And this is so important, of course, because this is the mechanism with which all particles get their mass. So seeing the W mass align with Standard Model predictions was a hugely important confirmation for not only the Standard Model structure, but also the particular pattern of spontaneous symmetry breaking. Okay, so why is this hard to do? So the W decays primarily in 2 ways, either leptonically or hadronically. So in leptonic decays, let's say we have a W plus, it'll decay into a lepton of any generation and its corresponding neutrino of the same generation. And so this will happen about 30% of the time we have a W go into this leptonic final state. Okay, hadronically, what we have is the W connects the up and down generations. So really what we'll see experimentally is that it goes into hadrons because QCD exhibits confinement, so we can't observe the individual quarks. But what's happening really at tree level in this diagram is that we have an up and an anti-down quark of any generation being produced. So this happens about 70% of the time. Okay, and so why this is really hard to measure experimentally is the signature for something leptonic. We actually can't see neutrinos in a detector. Neutrinos just take the energy and carry it off. So we need to understand what's missing by looking at the missing energy of their system. And more specifically, because when you collide 2 protons with each other, the PDF of the partons in the protons are going to not conserve momentum along the beamline. So we really can only look about things transverse. So we know that the net transverse momentum before the collision is going to be 0. So afterwards, we know that the net transverse momentum should also be 0. So any unbalanced net momentum in the transverse direction, we assume is carried off by neutrinos. So there's already a couple of steps in reconstructing this experimental signature. Then when we think about hadronic stuff, because of the confinement of QCD and because of the hadronization, we have these whole messy jet objects, which are very hard to fully reconstruct. They're extended objects. They have a lot of different particles inside of them, and they're just holistically much messier. So the reason that it's so hard to have done this measurement is that there's really no clean bump hunt, right? You often think that you just want to do an invariant mass search where you look for an excess in a mass of a particle, but clearly that can't be done here because jets are too messy and neutrinos disappear. So that's why W is something much more difficult. So if you want to compare to a much easier case of something like a Z boson, which decays into things like this, you can basically just look at the invariant mass of your dilepton system, and you'll see, you know, Standard Model stuff happens, and then there's just this big bump right at the mass of 90 GeV. That doesn't happen for W's because, again, we're missing one of the particles. So the way that we do the measurement for W's is, again, we want to look at leptons. And that's because leptons are much cleaner than jets. We can actually observe their momentum. And what we do is we look at the distribution of the PT of this lepton. So basically what's happening, this is the probability. We look at the PT spectrum of our lepton, and we see that there's some features that we understand. So the mass of the W, without getting into too much specifics, should be about 80 GeV. Okay, and so that means there should be some Jacobian shoulder that happens in this distribution, where if we have the W decaying at rest, we expect that at most, for these quasi-massless particles, we would expect it to carry away roughly half of the energy in terms of its momentum. So we expect this shoulder to show up basically at the mass of the W over 2. Okay, and there's some more subtleties to this distribution, but basically what we're doing is we're fitting this distribution in the PT of the lepton to match on to what we would expect given the standard model predictions. So it's really just going to be a precise fit done on the PT of the leptons rather than this very clean missing mass or excess of the dilepton mass peak. Okay. So then there's some uncertainties that show up in this, which are really important. Okay. So clearly, in order to calculate this mass, some of the things that we need to figure out is the total width of this particle. And of course, this depends on hadrons. So anything that involves QCD becomes quite difficult. We need to do some lattice predictions, things like this. So there's a lot of uncertainties built in to the actual measurement of the width of the W. Things that are also uncertain are the PDFs of quarks in the protons. Okay, so if we're producing a W or if we're decaying a W, things that we need to know are the PDFs of this particle, of the particles that produce the W to some very good precision. Otherwise, we can't calculate this spectrum up here very well if we don't know the initial energy conditions. So the fact that we have uncertainty in terms of QCD plays into the fact that we have uncertainty of the W mass as well. So a lot of these standard model effects are really kind of tangled up into each other. And so as we learn more about the standard model, the precision of this measurement will improve as well. So there's really a lot of subtleties kind of hiding in this measurement. Okay, so I want to summarize the current state of W measurements. Okay, so if we think about the mass of the standard model value, this is going to be 80.357 plus or minus 0.009 GeV. Okay, so for a standard model prediction, we already have a very small error bar on it. And we have this value of about 80.3 defined here. So it turns out that the other measurements that have been made, so other big experiments that have done it are LEP, which is a lepton anti-lepton collider that was at CERN. We have the SLC, which was the collider at SLAC. And we have previous CDF measurements, which again is Fermilab. So there's all these big experiments, and of course, sorry, LHCb plus ATLAS as well, that have made these measurements. And so a few of these measurements, I think only one of them actually, has sort of gone below, but with error bars still fitting in the standard model region. And it turns out that more of these measurements, in fact, have been pulling to the right. So by the time we get down to the CDF measurements, which happened most recently, the CDF measurement is really concerning because not only does it sit at a much higher mass value, but it has extremely small error bars. So the CDF2 measurement that was reported recently was 80.433. Oh, sorry, this was 6, not 9. Okay, so I was even a little bit grandiose with these error bar cartoons here. Okay, so this is troubling because again, not only is it so much higher of a value than what we predict for the standard model, but the error bars that they're claiming are extraordinarily small. So this could be potentially some problem. So if you want to just take this value and interpret it, this is where you get all these crazy headlines saying that, oh my God, this is our 7 sigma anomaly that's occurring. What is going on, blah, blah, blah. But of course, that's not a particularly fair assessment if you want to consider what the actual world average of measured values of the W masses. That's a much more responsible figure to quote. So if you take the world average of our W mass measurements, then you end up with something that's much more like less than a 3 sigma tension with the standard model. Okay, so really we end up with something that's a little bit more like this. Okay, so the 7 sigma stuff is kind of hard to believe, but certainly there is some truth in the sense that all of our measurements of the W recently have been pulling towards larger values. So what new physics contributions potentially are we missing? What standard model contributions are we mismodeling that are pulling this mass value up above what we currently think it should be? Okay, so maybe you're a little bit skeptical about what's going on with CDF. So if you aren't, let me make you a little bit skeptical first. So CDF collected data from 2002 to 2011. And for reference, in case you have forgotten, this year is 2022. So perhaps it's a bit surprising to you as to why this data is being analyzed so much later. Fair point, I have this question as well. Certainly some important improvements in the way that they do the data analysis have been made in the past decade. So that might speak to why they took so long to do this. So they took this data at the Tevatron. That was what was at Fermilab. And unlike the LHC, it's not a PP collider, it's a P anti-P collider. And the center of mass with which they collect the data was a little bit lower. It was only at about 2 TeV compared to the 13 TeV that we run the LHC at currently. So clearly there are some differences in the kind of data that's being taken here versus at LHCb and Atlas. So the things that they claim that have improved, because again, they have a previous measurement that wasn't nearly as far to the right as this current measurement is. The things that they're claiming improvement are a 4 times amount of data. So they had like 2.2 inverse femtobarns, now they have 8.8 inverse femtobarns, which for the record is still not a huge amount of data to be analyzing for something like this. They also claim that in the past 10 years, the PDF uncertainties have fallen quite a bit. And also the track reconstruction, so basically the precision with which they can measure this PT of the lepton has improved quite a bit as well. So basically they're claiming that they're squashing this number here, the uncertainty, by all of these improvements. But obviously all of these things are just saying why they can make a more precise measurement, and it's not explaining why we should have so much bigger of a mass measurement than before. So for the rest of this talk, what I want to do is I want to focus on understanding how this fits in to the picture of the standard model and how we can potentially explain this anomalous shift upwards using some new physics models. So this is kind of the history experiment side. Any questions so far on this? Okay. So the next part that I want to focus on is this idea of doing an electroweak precision fit. Or sometimes people will abbreviate this as EWPT, electroweak precision tests of the standard model. Okay, so the idea of this is nice and straightforward. The idea is that we're going to leverage very precise measurements that were made on other aspects of the standard model in order to make more precise predictions for observables that depend on these things. Okay, so let me break this down a little bit. So the standard model has 3 parameters, right? So apologies if this reminds you too much of your first week of QFT. But of course, the idea is that we define our symmetry groups. We write down all gauge invariant terms. And then we have some number of measurements that we have to do to be able to make predictions. And then once we've made these set of measurements, we can use those measurements to then predict values and search for those values experimentally. So we have some set of measured parameters. Which in turn can calculate and make predictions for the other observables in the standard model. Right. So the idea is that we take very well measured parameters. And we use them to make predictions for things that are hard to measure. Like, for example, the W mass. So the idea is that we're going to be leveraging these very precisely measured standard model parameters and using them to calculate what the mass of the W should be. So of course, this should first just be a standard model prediction because we are making the prediction of how it depends on other observables based off of the structure of the standard model. So the observables that we are going to be using that are well measured, I'll leave on this side, are going to be the fine structure constant evaluated at the mass of the electron. So this is extremely well measured. This is a number that we all know and love. Okay, so this is something that we know very well. And another, which is called G Fermi, which basically acts as the high energy or the low energy effective theory for a Fer fermion interaction. So let me write down this number. It's 10 to the -5 inverse GeV squared. Okay. So what this number is, if you haven't seen it before, the idea is if you just want to write an EFT for Fer fermion interaction, notably like the muon decaying or something like that, you have your incoming lepton, you collapse all of whatever could happen into some coupling called G Fermi, and then you have three leptons coming out. So clearly this is a dimension 6 operator. So we need to have something of energy dimension to the -2 showing up here. So that's what this G Fermi is. And again, it's extremely well measured because this is a low energy effect. Okay, so some other very well measured observables that we've been able to collect at experiments over the past decade are the mass of the Z, because again, we can do that simple bump hunt, the mass of the top, the mass of the Higgs, the strong coupling at the mass of the Z pole, which is where the LHC runs, and the correction to the fine structure constant after you run it up to a higher energy scale using hadronic correction. So this might seem like a specific thing to have measured well, but it is what it is. Okay, so these are the observables that we've been able to measure extremely well at experiments. And so what we can do is we can then write all of these other observables that we want to understand as functions of these well-measured things. Okay, so now observables to predict, we'll have a different set of observables that will depend on these things. And this includes things like the width of the Z, the width of the W, the hadronic cross section, forward backward asymmetries, things like this. So there's a lot of other things, of course, in our standard model that we would want to measure, which we calculate from these observables. So of course, one of the ones that we're most interested in today is the W mass. And so if you do your standard model shenanigans, you find that you can write down the W mass as a function of these observables in the following way. Okay, so before we take loop effects, basically you just have, this is your primary contribution. So all this is telling you is a direct probe of tree level spontaneous symmetry breaking, right? This is just telling you how we would expect the W to get a mass using this Higgs mechanism. And then this delta R correction is something that's been well calculated throughout the years. We've calculated up to this order and perturbation theory. And basically it just tells you these loop corrections to W mass still given standard model effects. Okay, so all of these things can be written in terms of these well-measured 5 parameters here. All right, so the goal of the electroweak precision fit, or the EWPT, is to then take our well-measured variables and float the variables, which again are the ones that we just mentioned. So blah, blah, blah. And what we want to do is then we want to include the standard model predictions and the experimentally measured values of these things. And we want to throw them all into a fit. So we want to measure when we can minimize the chi-square value of this term. Okay, so let me break this down a little bit. The idea is MJ is the experimentally measured value. OJ is the standard model calculated value, which is again a function of these floated variables. And then sigma J is the experimental uncertainty. Okay, and so the idea is, since we're floating all of these variables and we're minimizing over chi, is we're finding the minimal discrepancy basically that we can. So given these values of our variables, what is the minimum chi-squared value that we can get by tuning these for the various standard model observables that are functions of these things, right? So does that make sense? What we're trying to do is we're trying to leverage how precisely these float variables are and turn that into concrete predictions for what the rest of these observables should be. Okay. So we can include these various observables of interest either as part of the fit that we're doing, something that we're floating like we are over here, or something that's part of the calculation. So if it shows up here or in the floats, that's just kind of a matter of decisions. This is not a super fixed process. You can sort of change it around and change what variables you want to include in your fit. So if we want to compare the standard model prediction of WMAS, what we would get out of this electroweak fit before is that we'd have WMAS to be about this 80.35, which I showed you before. And so the p-value of this was about 0.45. But as soon as we put in the CDF2 result as our value of the observed quantity for the WMAS, now we get a p-value of like 2 times 10 to the minus 7. Okay, so clearly what this is telling us is that the standard model as we interpret it so far is likely not the correct model to understand this WMAS fit. Okay, and if we want to be a little bit more charitable, we can do the world average. We have something like 10 to the minus 4 or something. So that's again that 3 sigma rather than this insane 7 sigma that we're claiming. But the point is that if we really believe that the mass of the W with the CDF value is like 80.43 instead of 80.35, that's a huge amount for this value to be dragged upwards. And so the standard model as we interpret it right now is likely an incorrect model of what's going on. Okay, so given that the standard model is wrong, how do we fix it? What do we add to it? How can we adjust this correctly? So the idea is that we want to introduce these additional variables to float in our fit that we call the oblique parameters. Okay, and the idea is that these are parameters that show up as corrections to the vacuum energy or the propagators, or the vacuum polarization, or the propagators of our particles. Okay, so that's why it's called oblique. These are particularly interesting corrections to include because they're going to be gauge invariant and they're going to be finite, which are both important aspects to have when we're doing things that, as you will see, include higher dimensional operators. So the point of this is that we're going to choose a basis of higher dimensional operators that directly affect the mass of the W and the Z. Okay, and this is important. You might think, why are we caring about the Z mass? The Z mass is fine, it's measured well. But again, if we go back to this idea here about how we understand the mass of the W in terms of standard model parameters, is that the W mass and the Z mass are very intimately related. So what we measure to be the Z mass versus like the bare parameters that show up in our standard model, they might be different. So if we have some theoretical correction to the Z mass that changes this relationship here, it might not show up in the physically observed Z mass, but it will definitely show up in how we measure the W mass in terms of these parameters, right? So the Z mass and the W mass are very intimately connected in this way. Okay, so let me introduce the oblique parameters, the bases that we're considering here, which are the Peskin-Takeuchi parameters. And very frustratingly, they are also called ST and U. They have absolutely no connection to the Mandelstam variables. I'm so sorry, I didn't come up with this, but okay. So they're called ST and U, but capital ST and U. And the idea is that we can kind of think of these things not only as these corrections to the propagators, the vacuum polarizations, but we can also have an interpretation where these things map on to these higher dimensional operators. So we can also sort of see them as relics of some higher dimensional theory that we need potentially some new physics to complete. Okay. So if you recall, propagators, or these vacuum polarizations for massive particles, we just have some line, and we'll define our propagator, for example, our Z propagator, to have this this index structure. Okay, so if we want to measure corrections to this, we'll have sort of our tree level stuff. And then in order to make sure that these things, again, are going to be gauge invariant and match on to this index structure, is we'll have some correction. And all of these terms that we calculate for the Peskin-Takeuchi parameters will be proportional to this momentum mu term here. So really what we're going to see are all these corrections that can be absorbed into the vacuum polarization like this. Okay, so what these parameters are going to look like, the definition. Bear with me for a second, they're a little bit ugly. So for the S parameter, this involves the derivative, which makes sense because, again, we're talking about things proportional to momentum, of the neutral gauge bosons. So terms like this propagator ZZ means that there's a Z incoming and a Z outgoing. But of course, you can also have corrections that look like this. You have a Z incoming and a photon outgoing or something like that. So note that this can only happen for the neutral gauge bosons, because otherwise you would be violating gauge invariance if you have something uncharged going to something charged. So the S parameterizes how we can affect basically the masses or the propagators of these neutral bosons. T measures instead how we can change the masses of the weak gauge bosons, so the W and the Z. And because these are massive things, we can evaluate their vacuum polarization energy with zero momentum going through the diagram. Okay, so that's T, a little bit simpler. And then there's one more parameter, U, which is a little bit harder to understand. So I'll write this out really quick. Okay, and so again, the point here is that all of these things are going to be the propagators tying these two gauge bosons together. CW and...
Excuse me,
yeah.
Can I have a question for more
Absolutely.
details about the derivation? So in the usual Feynman diagram, this vacuum polarization is kind of canceled away, and we only compute this connected diagram, right?
Right.
Yeah. So
yeah,
here, so here, what's the framework to include this vacuum polarization? What's the general framework?
So, the point is, I think basically the point that they're going for with this is that we'll assume that like everything has been like everything is done at tree level, and all of these things are supposed to be loop level corrections to it. So the original values that they're assuming for the propagator are just assuming just after spontaneous symmetry, and then all of these corrections that they're looking at that are proportional to this term, proportional to the momentum, that's going to be the higher order effects that they're considering. So, right, you should think about this as the original propagator is just the tree level thing. And so what's interesting is that, you know, in the actual standard model, because we have loop level corrections to things like the Higgs and heavy quarks, these parameters shouldn't actually be non-zero in the standard model. We've kind of changed them to renormalize for the loop corrections. But yeah, I think the way that originally Peskin and Takeuchi were thinking about this was that we just take our propagator to be the tree level thing, then all loop level effects can be parameterized in this sort of way, if that answers your question.
I see. So, in principle, you still only compute this connected diagram, right? Just by including this high order terms.
Yeah.
I see. Okay, thanks.
Yeah, cool. And I'll give like an EFT interpretation too, if that's more useful for other people in the audience. But yeah, so just to explain really quickly, what these S and W are is the cosine and sine of the Weinberg angle, which basically tells you the amount of mixing between the SU2 and the U1 symmetries in the standard model. Okay, good. So on that note, thinking about these things as EFT operators, we can think of these things as coming from these kinds of diagrams. So S is going to be like a parameter on these dimension 6 operators. So we'll have a Higgs connecting to the field strength for the SU2 and the U1. So again, all of these things are the gauge fields of the original symmetry of the standard model, not after spontaneous symmetry breaking. Okay, and so this should make sense given what I said before about how we just tie the neutral propagators together, because again, clearly this can only tie the neutral components of these things together in order for it to be a gauge invariant thing. So hopefully that is somewhat intuitive. And then we can also have this T parameter, which I wrote down, which is another dimension 6 operator, where we have the Higgs acting like this. Okay, and the U is this term here. So note that these two terms are dimension 6, and this term is dimension 8. So that'll cause a problem, but let me just get to explaining the T parameter a little bit more. So if you look at this term here, inside our covariant derivative, we have things proportional to our Z boson. So basically, if you expand this thing out, this is going to tell you, and you replace it with the VEV after spontaneous symmetry breaking, this term basically just gives you mass corrections to the Z. Okay, so again, it's not that the Z boson is going to change its physical mass, but instead the W mass dependence on what we believed the standard model Z boson to be will change. So while it looks like this will naively just change the mass of the Z, it'll just change the standard model dependence of these things, which will in turn change the mass of the W as well. So because it is charged, this is the term that can directly contribute to the W mass as well. So certainly saying that, I'm sure you're looking at this U term and being like, okay, but clearly this also ties together the Higgs and the W field, so why doesn't this contribute? Well, the reason that we're not so concerned with U is more phenomenological than EFT is very hard to construct a dimension 8 operator that has a bigger effect than a dimension 6 operator. And moreover, note that all of these things are suppressed by a factor of V squared. So that means if we want to have the U showing up, it's going to have an extra factor of V squared over this new physics scale showing up to make it a dimension 8 rather than a dimension 6 contribution. So when we do that, that means that anything that's running inside of the operator of the U is going to be even further suppressed. So in order to get a big value of U, if that matches what we would expect it to be, we're going to need much lighter particles. So U will correspond to having particles that are effectively too light in order to have not been found. So we'll get to this later, but basically the point is that U is dimension 8. It's very hard to model build in a reasonable way why U should be as big of a contribution as S or T. So really we're going to be focusing on T as the thing that can change the mass of EW. Okay, so if we go back to our electroweak fit, now the mass of the W is going to have the following correction. So the value that I wrote down before of the mass of the W in the standard model, okay, and it's going to have the following effects. So we're going to get a new contribution that'll look like this. Okay, so now what we want to do is we want to go back and perform our electroweak precision test, but we want to include this as the dependence of on our standard model parameters as well. So instead of just having the variables that we had before for our fits, now we're also going to include S and T as the parameters that we float. So the idea is we want to float all of these things to make sure that we're returning the minimum chi-squared, and then see what non-trivial values of S and T we would need in order to make the CDF2 measurement consistent with what our standard model plus S and T predictions of the mass should be. So now what we do is we want to perform our fit. And we're going to inherently set U equal to 0. If you're interested more about the effects of U, we talk about it in our paper. We find that it's actually, U tends to want to absorb all of the corrections. But again, since that's so hard to model build, not particularly well motivated, we just want to set U equal to 0 and focus on the effects of S and T. So let me show you the results of our fits. Okay, so standard model with old mass of the W world average, we expect S and T to be a little bit non-zero in their central values. Okay, so where should that be here? This is the PDG, so that includes the world average of these values. So you see this blue contour corresponds to the 2 sigma contours around the central value for our fit in S and T. So at 0, 0, which is about right here, this is a point that you would expect if there was literally nothing that we missed in the standard model, like no higher hadronic corrections or no loop effects that were missed. We would expect these things to be 0, 0. So the fact that this is already off 0 and the central value is closer to here, that tells us that perhaps there was already some tension in the standard model and there was already some suggestions of new physics. Okay, but then if we start considering the effects from the CDF2 measurements, so now if we want to take the CDF2, that's this contour up here, and the other contours correspond to various combinations of the mass. So let me just point out the 2 most extreme situations for brevity. But you see that the CDF2, just taking that mass measurement, would put the central value somewhere up here. So there's this huge shift in S and T that suggests that there's something missing, okay? That our fit is much better minimized when S and T become non-zero versus when they are centered much more closely to 0. So with our CDF2, just to give you the official numbers that we fit for, S is equal to 0.17 and T is equal to 0.27. So clearly things are shifting quite a bit in S and T. Okay, so what does this mean? It means that we're really suggesting that T should have these non-zero values. So perhaps there's some new physics contribution that's giving us, in the low energy theory, an operator that kind of looks like this. So for the rest of our paper and the rest of our talk, we kind of explore what sort of new physics contributions could contribute to an operator that looks like this and shift the mass upwards so positively. So are there any questions about the electroweak precision test aspect of this? Is it clear what S and T are doing?
Question.
Yeah.
Compare with this fit S and T parameters versus the previous one that you mentioned about this 3 sigma to 7 sigma, this W mass. It seems to me like this one suggests the PDG data is it's kind of a more isolated from other group of data. For example, the LHC, LEPT, TV, and the CDF2 somehow is more close to each other, right?
Yeah.
But earlier,
so I mean,
W mass seems
good.
like the CDF2 is more separate, isolated from the others. So why is that how can I interpret this?
Yeah, so this is a great question. This is kind of the puzzle as to why CDF2 is so far. So let me unpack a little bit more of what these different classes are saying. So the PDG was just the existing world average. So as I mentioned before, we were already getting some pull upwards in terms of our value of the W mass. It was already a little bit too high for our standard model expectation, which is why this blue curve down here is not centered exactly at this 0, point. This yellow curve is taking like a new world average where we consider CDF2 to be included in all of the previous measurements. So that's why this yellow curve here gets pulled up quite a bit as well. So now its central values are something more like this. And then this green curve, CDF2, that's when we take the CDF measurement and we just double the error bars to see if we get something more reasonable by not changing the central value, but just saying that perhaps they underestimated their uncertainty. And we see that this then just corresponds to having a central value somewhat more like here. So basically, the shift upwards in the dots is how strongly we include the CDF measurements. So the point, yeah, like you're saying though, but there's definitely the fact that this blue contour, the PDG previous world average, is already not centered at 0, suggests that, there already was some tension in the standard model. So even if you don't necessarily believe the central value that's being reported by CDF2, there's certainly some experimental consensus that the W mass is higher than we expect. So beforehand, maybe it was easier to be like, oh, there's just some strong QCD effects that we're not considering. But now that it's getting pulled up so significantly, there might be something else out there.
Thank you. Thanks.
Yeah. Cool. Okay, so now let me move on to maybe the most exciting part of the talk. Where I can't spell. Interpretation. Okay, so how can we potentially interpret this anomalous value of S and T being much greater than 0 than we would expect? How can we attribute this to a new physics effect? Okay, so the focus that we're going to have is on the world average, meaning that we're including the results of the LHC, the SLAC, and the Tevatron. So this was that sort of intermediate curve where we include not only the previous measurements, but also the CDF2 measurement. So this is something maybe a little bit more charitable because again, we're in that 3 sigma anomaly versus a 7 sigma anomaly range. And so S and T for the purposes here will be 0.12 and 0.2 are the best fit values in our electroweak precision fit. Okay. So we want to do some sort of order of magnitude estimation as to what new physics scale should be contributing to these things. So again, if you go back to our EFT interpretation, we expect T to scale like V squared, which is the Higgs web, over 2 alpha times 1 over lambda squared, where lambda is our scale of new physics, right? So if this is the coefficient on our dimension 6 operator inverse, we need this extra factor of new physics scale to the -2 in order to make our dimensions work out, right? So very back of the envelope. So in order for T to match this value here, this is going to be approximately 0.2. And what this corresponds to is a new physics scale that's going to be of order TeV, if you want to consider a loop, or sorry, a tree level effect. And if you want to consider a loop level effect, then you need to include also the loop factor of 1/16 pi squared, right? If we want that to be equal. So that will bring down our new physics scale to being order maybe hundreds of GeV. This is loop. Okay, so the loop level is a little bit dangerous because when we have the LHC now, well, LCH, geez, the LHC, this is going to run 10 to the 13 TeV or whatever. So anything that's kind of down here and there's hundreds of GeV, we would expect to find. So if we run the LHC at our high Lumi and we still don't see it, that could be sort of a dangerous new physics theory to go down. However, because the LHC is made of composite particles, right, the actual collision energy of these things, the S hat of the collisions, is usually much less than TeV scale. So anything, especially if it doesn't have a color charge that sits at like the TeV scale of new physics, might still be rather invisible to us at the LHC. So this potentially could motivate why we would want to improve the energy frontier. But that's a story for a little bit later on in the talk. But essentially, because we want to focus on these new physics scenarios that wouldn't be ruled out by collider constraints already, we want to see if there's any new physics contribution that can occur at tree level rather than loop level. So to talk about this, I want to consider a specific model which is the singlet triplet scalar. Okay. So you might have heard this referred to as the triplet scalar, or if you're sassier, you may have heard of it responded to as the Swino. And what this is a particle whose charge under the standard model gauge group via singlet, triplet under this SU2, and again, a singlet under the hypercharge. Okay, so let's take this new particle and put it into our standard model Lagrangian. So now we'll have a kinetic term with covariant derivatives, an explicit mass term, and we'll also have at least a cubic term of interacting with the Higgs. Okay, so maybe you can also have a quartic term, but we're assuming that anything quartic will show up with a much weaker effect than anything cubic. So this is really all we need in order to make this work. Okay, so you might already look at this and understand where this argument is going. Because if you remember the story that I told you earlier on, it's the fact that the covariant derivatives have the gauge fields inside of them and that they act on a scalar that gets a VEV, which gives them a mass. So the fact that you're already seeing this term showing up and this thing can get a VEV, this should tell you that there should be some positive contribution to the mass that's going to happen. But let's work this out a little bit more carefully. If we want to calculate the VEV of this thing, then we can do this standard minimization and we find to first order, what we're going to have is approximately b squared over mt squared modified by this dimensionful coupling kappa. So that's where this cubic term is important. So, okay, so this is important because also this physics scale can't drag up to infinitely high energies. We see that because it's proportional to the Higgs VEV, it's always going to stay sort of at reasonable energy scales. So it's not some new physics effect that's going to get arbitrarily dragged up to like the Planck scale or something like that. It is a controlled VEV that this thing will have. So given that this will occur and that we have this covariant derivative where the W can talk to this new scalar, what we find is that the W mass will have this correction where we have the Higgs VEV contribution from before. And now we'll also have this phi VEV contribution as well. Okay, so again, this is from the Higgs and this is from phi. So if you assume something reasonable like kappa over mt is small, or not less than 0, geez, is less than 1, then you can find that the correction to your W mass will be of order kappa V over mt squared times the previous mass. Okay, so again, as long as the ratio of the coupling in the cubic term is smaller than the mass of the particle itself, then we expect that we'll have sort of this almost order 1 shift in this variable. So if we translate this shift into what T should look like, our oblique parameter T, then we can plug in, oh, just alpha. No, it should be alpha squared, I'm sorry. Mt to the 4. And in order for this to work, again, we need this to be about equal to 0.2 to match our electroweak precision fit. Okay, and in order to see that happen,
Cari,
here is the, yeah,
a question,
range of
maybe
parameter space.
we mentioned,
what's up?
So we talk about this. Let me just make sure the triplet scaler, does he get a VAF? It seems earlier
Yeah,
you're
so
writing.
in order,
Does he break the
yeah, so
weeks?
we do assume that it'll, so it shouldn't break electroweak, because, yeah, I think it's because of the gauge structure. It doesn't break any of the electro. It definitely doesn't, like, the contributions it'll have will occur in these mass terms here. Let's see why. That's right. We did talk about why it shouldn't break electroweak. So it's not charged into hypercharge, so it's not going to talk to the neutral components. It won't break electroweak. I know the answer. I don't know if I can see it in this. Yeah, I mean, because
So
basically you can think about it. Yeah, so this is the VEV. You can
the joint
think about it.
representation of. What's the 3 components that which component you are choosing to have a VAF? So the
Yeah.
standard
Yeah.
will break to U1 down to U1 EM, but now you still have a triplet scalar with some VAF.
Yeah, okay, so you're saying what happens to the other degrees of freedom for the scalar?
Yeah, I'm just trying to make sure it does not break U1 EM.
So I mean, I think the point is that where this broken degree of freedom would go is that it works with the Higgs, like the Higgs in this particle can now mix, and that'll cause the W mass to shift upwards, W and the Z mass to shift upwards. So it'll just change the longitudinal degrees of freedom of the W and Z, I think is how the degrees of freedom get reorganized. And so that shouldn't affect the photon, like the photon should still remain massless. But yeah, I think that's how this should happen.
But do you have a preference on how? Do you have a preference on how the phi has a VAF? Like you only write down the condensate, the value of that, but which component you are choosing to have a VAF? In the
yeah. Ooh, well.
It's just the neutral component that gets a VAF.
Right. It has to be the neutral component in order for it to not break anything else. Right. So yeah, I think that's the secret, right? Is like the neutral component gets the VEV, that's the thing that gets reorganized into the longitudinal degrees of freedom, like the Higgs. So now it's some mixed state between like the Higgs neutral component and this neutral component that act together to shift the mass upwards, I think is the story here, right? Because we're not introducing any new gauge symmetries, so there shouldn't be any like additional fields floating around that way.
Okay, But the triplet scalar does not carry the U1 hypercharge.
Right.
Okay. Well, I assume that.
Right, because since it's a triplet, you can think about it like the spin 1 state, so it can be like +1, 0, -1, right? So it's the 0 spin matrix under the SU2. So that would be like the neutral degree of freedom, right? Sorry, Howard, what were you saying?
If this were the only scalar, the photon and the Z would remain massless, and you'd get a mass only for the W.
Right.
I assume maybe what I imagine correctly. So there are some, let's say the electroweak in the target. There are some SU2, and the standard model Higgs is the doublet of SU2, the fundamental, and then you pick out some VAF. But that one you do have U1 hypercharge, and you break down to U1 EM. But here the triplet scalar, somehow this condensate should also align with that condensate of the standard model Higgs in order to not break anything further. And that target space is more like SO3 in terms of a global structure, because there's a triplet. These are the join of SU2, and which is a vector representation of SO3. But I suppose one need to find out such a direction of the condensate without breaking anything further. And what you say is that you have a way to find that direction, but there should be some restriction on how you choose the path.
Well, right? I don't understand why you're concerned beyond the fact that we just choose the neutral component of the scalar.
Neutral on the SU2 and the U1. Neutral on the what? Neutral on the U1 EM.
Yeah, so I mean, like there will be like the neutral component of phi in the SU2, right? Which will also be neutral in the SU2 U1.
There's some constraint on the signs in the potential that guarantee that this is aligned properly, but it's rather trivial.
Yeah.
Okay.
Yeah, so I've chosen the signs in a conspicuous way to make sure that we get the VEB that we want.
Okay, thanks.
Maybe we can chat more. Yeah, if you still have confusions after. Because I am now over time. Well, I guess technically there's no overtime, but I'd prefer to not keep you all forever. Okay, yeah, so given this model, all right, I'll just pull up a new one, that's fine. Here's the contour of allowed space that we can have. So basically, again, as long as you're trying to make sure that this stays roughly order 0.1, here's the constraint that we have on kappa, the coefficient on the cubic term, with the mass of the scalar particle. So what's nice is, again, you can see these things sort of go up to the TeV scale. And of course, there's some unitarity bound that will cut things off at higher energies, but we didn't worry about that in this paper. So as long as this is a little bit smaller, order hundreds GeV rather than TeV, we can have something that not only will escape collider bounds currently, but also is a reasonably natural theory, right? We're not fine-tuning any parameters to be particularly big or small in order to get this result to work out. So the triplet scalar is a really interesting possibility here. So one more example that I want to give really quickly is this idea of singlet doublet fermions. And the idea is that we introduce NF species of singlet fermions. So Majorana masses plus doublet fermions, where we have these two Weil fermions to make up a Dirac fermion in our theory. So now basically we'll have these interaction terms that are Yukawas. So again, we can correct this higher dimensional T operator. And once we have these operators, then what we can do is we can contribute to the propagators with loops of these fermions showing up. So let me just give you sort of a taste of what parameter space we can do as long as we're introducing these singlet and doublet Weil fermions. If we only have one family of these things, it's kind of dangerous. So this is our available parameter space. And since we're in like the hundreds of GeV, this is something that could very well be constrained by colliders already. This red region are things that would affect the width of the W or of the Z and the Higgs. So we're trying to not look in that space. But overall, just having one family of one singlet and one doublet fermion added to the standard model, we can't really do something that hasn't been explored by colliders yet. But if we increase the number of species of these things, which, albeit is a little bit ad hoc, then we can really push into a lot more available parameter space. So this is something that looks a little bit more promising. Now we're considering we have 4 different species of these particles, and we can push into things that are closer to a TeV scale. So this would have to contribute at loop level rather than tree level, which is why the mass scale of interest is like these hundreds of GeV rather than TeV. So the triplet scaler is something that works out to be a little bit more natural in terms of correcting. But okay, there are some other models that, of course, we can consider. And since this was a big ambulance chasing phenomenon, there's plenty of other papers that include another million possibilities of new physics. Although I would caution you to take every paper with a grain of salt, because like this one, they were all written in the scope of a couple days. So yeah, when reading these literatures, I would be a little bit skeptical. Great, okay. So now to conclude, the CDF collaboration reports a high value of the mass of the W. And while this is sort of anomalously high, again, the global average is still high. And it was high before we included this as well. So there's definitely been some indications that perhaps our standard model prediction for what the W should be is incomplete. And moreover, it's not just the mass of the W, but it's other electroweak precision test observables were also 2 or 3 sigma tension with standard model. So if you're skeptical that the CDF2 measurements isn't incorrect, there's other indications that perhaps there's something missing in the standard model, that there's some other tensions that are occurring. So there might just be some new elements of new physics or something mismodeled, or some ways that we can improve just modeling hadronic contributions and things like that. But of course, since I'm an optimist here, I wanted to think of this as a sign of TeV scale, new physics, possibly. Okay. And in order to really tease out these signatures in a way that's concrete, and we can actually identify the new models that are contributing to this, really the right way to be probing these things is to be constructing higher energy colliders. So to me, this is another indication as to what the future of particle physics should be, and that should be our goal, to expand the intensity and the energy frontiers of these colliders. So if we really want to flesh out and understand not only new physics, but also our standard model predictions better, future high energy colliders are certainly the right way to be looking for the field. Okay, so with that, I will conclude. Thank you so much.
Thank you very much.
Any further questions?
Thank you for the wonderful seminar. Question from the audience? Comment? Please feel free. Cari, what would you expect next things in the next few steps in the near future, maybe next 5 years? I don't know whether there's something. Next 5 years, yeah. I mean, so right now, the only experiment at the LHC that have W measurements are LHCb and Atlas. So it'd be awesome if the CMS could finish up their W mass result as well. So that would be another, benchmark in this global fit. So if they also see something systematically high, then that's further validation. But if they see something low, then that's really interesting of like what assumptions are these other experiments making that these aren't. So I think any kind of answer that CMS could give us by doing this measurement would provide a little bit more of a theory prior as to where we should be looking for what's missing.
something that I think is more like a 50-year goal. I think that building a muon collider would be a really fun way to test for this. So muon colliders, because they have muons, which can radiate things like W's or Z's or whatever as initial state radiation. These things are really good probes of electroweak physics. So having a high energy muon collider would be able to not only give us a really clean TeV scale experiment, but also something that directly talks to electroweak stuff. So I do think that if any sort of anomaly persists in the electroweak sector, a muon collider at high energies would be a great way to address it. So that's sort of where I'm hoping the field kind of converges in the next couple of decades. But yeah, I mean, whatever CMS is, I think will be really interesting.
I wouldn't hold your breath though, because the LHC is such a messy environment that it's hard to imagine that they'll do much better than Fermilab.
That's why we need the muon collider, right, Howard?
Excuse me, can I have one more question?
Absolutely.
Yeah, so in your approach, you assume there are like a high order term, which is not renormalizable. Yeah, so I'm wondering if we assume like the Higgs particle is, yeah, it's not fundamental, do we also get a similar corrections, or the story could be different?
Yeah, so I mean, I think, and I mean, Howard would know certainly better about this than I would, but a lot of the interest in doing these electroweak precision tests before the Higgs was discovered was understanding like 2 Higgs doublet models and Technicolor and things like that. So I think the contribution would be a little bit different. So really nailing down if this was the correct pattern of spontaneous symmetry breaking, and these were the correct standard model inputs to be using to get these sort of electroweak precisions was really important to discovering the structure of the Higgs. So I think a composite Higgs would give a slightly different result. Am I wrong here, Howard?
Basically, the T parameter is some measure of how much your custodial SU2 symmetry is broken. And anything that breaks that will contribute to T. And so it depends. In fact, the composite Higgs models are generally constructed very carefully to avoid big contributions to T, sure. But you can certainly relax that.
Yeah, okay. So model dependent, I guess, like everything else in life, but yeah.
Thanks, Cari. Bye-bye.
Thanks, Howard. Yeah, thanks, Stephen. Thanks,
Cari,
everyone.
Thank you for the wonderful seminar. Thank you very much. Thank you. I'll see you. Goodbye.
See everyone.